Let's look at another antiderivative that uses an adjusted substitution technique. This particular technique is called miscellaneous substitution. It differs from our previous technique in that we're not necessarily looking to make the integrand table ready in the sense of finding a u and a du. Here we basically transform the entire integral algebraically and with the help of the differential. So when we look at this particular integrand here, we're thinking, we don't have the u and the du in the standard sense. Now, I will say that integration by parts is another technique that you will learn in Calculus II that you could actually apply to this integral. But we're going to use a technique that actually utilizes the ideas that we have already spoken about. So let me also say this, how you set this up will vary. There is no one way to do it, but here is an illustration of how you can do it successfully. So what we're going to do here is look at the part of the integrand that's the most complicated, namely the square root. So here's what we do. I've had this written in red. U will be the square root of x plus 1. And now what we need to do is transform everything else in the integrand into a function of u. So first what we're going to notice, if we square u, we relieve ourselves of the radical. We get u squared is equal to x plus 1. First thing we can do is take the differential. So taking the differential of this equation will give us 2u du equal dx. I put this in that box. And now we need x squared. So what we can do is we can subtract 1 from u squared. That'll give us x, and if we square it out, that'll give us x squared. So x squared will be equal to u squared minus 1 quantity squared. Now again, this is not the standard setup, so we do need to go ahead and expand this. This is just a perfect square, so x squared will be u to the fourth minus 2u squared plus a 1. So now we have everything in the integrand written in terms of the u variable. So first what we're going to do is we're going to replace x squared with this, so that gives us u to the fourth minus 2u squared plus 1. And now the radical is just u, and the dx, as we've noticed here, is 2u du. So that'll give us the term 2u squared du. Again, very simple, very algebraic, not difficult, just a little bit different from what we're accustomed to doing. And now, of course, we'll go ahead and factor the 2 here. We don't need to have it cluttering up everything. And multiply all of these terms by the u squared. That'll give us a u to the 6th. That'll give us a negative 2u to the 4th. And then, of course, the u squared times the 1, just a u squared there. And now we could look at this and say this is table ready, but a very simple table ready. This is just the power rule, add 1 divided by the new power. So the integrals that you actually end up doing are quite simple. It's just the technique requires some algebraic maneuvering before that power rule application. So in adding 1 dividing by the new power, we get 2 times u to the 7th divided by 7. Here we'll get a negative 2u to the 5th divided by 5. And here we'll get a u to the 3rd divided by 3. Now, of course, you're thinking you can just substitute for u and be done. But what I wanted to show you is a method to clean this up and make the antiderivative look very nice. Again, it's up to you, but this is a technique you should be able to do. First thing I'm going to notice is that we've got a lot of clutter in here, and we've got some common factors that we can remove. So we've got a u cubed in everything, so we factor the u cubed. And of course, downstairs we have a 3 times a 5 times a 7, so we're just going to pull all of that out. Now when we do that, you keep it factored so you know how to adjust these. So we've got the 7 that leaves behind the 15, so we're going to have a 15u to the 4th. And then we got the 5 here, so that leaves behind the 21. So we have a negative 2 times the 21, which gives us negative 42u squared, remembering that we factored the u cubed. And then here, 3 is gone, but we're left with a 35. So the only thing here is just the 35. So this is nice and neat. At this point, we make the substitution for u. u is equal to the square root of x plus 1. So here we get x plus 1 raised to the 3/2 power. And then, of course, u to the 4th, what's nice about this, when we square this, we get x plus 1. But when we square it again to get the u to the 4th, we have x plus 1 quantity squared. So you have to pay attention to that. And then, of course, here u squared is just what? X plus 1, and then nothing goes here. Now, I went ahead and expanded the perfect square here. That's x squared plus 2x plus 1. So all we need to do is just do some simple algebra. So 15x squared, 15 times the 2x will be 30x, and 15 times the 1 is 15, and then distribute the negative 42. Negative 42x minus 42 plus a 35. And so now it's very simple. So this reduction is not very difficult. It's just something that's a little bit new. And then, of course, now if we look at this, we have a 30 and a negative 42. That'll give us a negative 12x. The 15x squared just drops down. And then if we look here, the 15 plus the 35 gives us the 50, minus the 42 gives us an 8. So our nice and neat antiderivative looks as follows: 2 over 105. Of course, if you multiply these numbers, you get 105 times x plus 1 to the 3/2 power times the quantity 15x squared minus 12x plus 8 plus the arbitrary constant. And we are done.